So welcome to week 2 of our chemical equilibrium unit. This week we're going to be dealing exclusively with calculations. We're going to look at what we do when we have equilibrium concentrations, kind of like continuing off of what we did last week. And then also looking at systems where maybe we only know the amount that we initially have. So let's start first with reviewing how to write out an equilibrium law. So to calculate Kc, we do need an equilibrium law first. So here we have a system at equilibrium. Kc is equal to products over reactants to the power of their coefficients. So my concentration of Hi is on top, and that is squared, divided by my concentration of H2 times my concentration of I2. Remember, we only include gases in aqueous species. If something is a liquid or a solid, it would not be included. Now we know equilibrium concentrations, so we can plug these numbers into our formula. I know my concentration of Hi is 1.87, and that's millimoles, so that's 10 times 10 to the negative 3. These need to be concentrations, but it's 1.87 millimoles in a 1 liter container. So that would be 1.87 times 10 to the negative 3 moles per liter, and that's squared, divided by my concentration of H2, which is 0.057 times 10 to the negative 3 moles per liter, times my concentration of I2, which is 1.07 times 10 to the negative 3 moles per liter. Kc doesn't have units. When I do this calculation, I remember to square that top number. I get 573. Now remember from last week, we can use this to kind of quantify equilibrium. Because this number is greater than 1, it means we have a larger number on top. So I would expect that this equilibrium favors the products, or the right-hand side. So there would be more hydrogen iodide present at equilibrium. Now here's a different question. And you'll see that there's some different information here. Here now, it tells us how much we contain, and then after 1 hour, equilibrium was reached. And it gives us an amount of 0.25 moles of CO2. When we do these equilibrium calculations, we need to deal with equilibrium concentrations. These are initial values, though. However, we can do that with simple equilibrium calculation. It's called an ice chart. Ice table. Dun, 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 dun. Ice table. What an ice chart is it allows me to find out the equilibrium concentrations. This is what we want. This is what we used in question number 1. We need these for our calculations of the equilibrium constant. We can do that if we know the initial concentration and if we know the change. Now the initial concentration we can find, right? That's just concentration in moles per liter. The change is important, and this comes from the mole ratio. Everything's going to change according to what the coefficients are. If you think back to last week when we were talking about the Haber process, we looked at the graph and we looked at those coefficients and we saw how they changed as a reflection of what those coefficients were. If something had a coefficient of 2, it changed twice as much. Coefficient of 3, it changed 3 times as much. So just using ice. So we are going to use an ice chart. So we have our reaction here, carbon monoxide plus HOH. That's a gas. That's important. If it was a liquid, I wouldn't need its concentration. CO2 plus H2. So things that we have initial concentrations. Now this is this much stuff in a 1 liter container, so my concentration of this is 0.750 moles per liter. My concentration of H2O is 0.275 moles per liter. And I don't start with any of this other stuff, so my concentration is 0 moles per liter and 0 moles per liter. Now this change is the most important step, and it's the reason why we use this ice chart. Now we do have something given to us in the equilibrium concentration. We know our concentration of CO2 at equilibrium is 0.25 moles in a 1 liter container. So that's 0.250 moles per liter. So that's what we know initially. Now we need to start working in this change row. And one thing we can see right away is my concentration of CO2 goes up by 0.250 moles per liter. If I think about my other product, which is H2, this one will also increase. Now the amount it increases by is going to be dependent on what the coefficient is. My coefficient on carbon dioxide is 1. On H2 it's 1 as well. So the amount they're going to change by is the same. So H2 is going to go up by 0.250 moles per liter. If there was a 2 in front, it would go up by double. It would go up by 0.5 moles per liter. And at equilibrium, H2 will be 0.250 moles per liter. Now these are my products. They're going up. I know my reactants are going to go down. The amount they go down by, again, is dependent on their coefficients. Because they also have coefficients of 1, they're going to go down by the same amount that CO2 goes up by. So this one's going to go down by 0.250, and this one will go down by 0.0250. So at equilibrium, I'm going to have 0.75 minus 0.25, 0.500 moles per liter. And my concentration of H2O will be 0.025 moles per liter. So we use this change column, or row, to determine how much they change by. That's dependent on the coefficients. And then we can find out what the equilibrium concentrations will be. Now I can calculate my Kc. Kc, again, is product, so CO2 times H2 divided by reactants, CO times H2O. So I do that calculation. So 0.25 times 0.25 divided by 0.5 divided by 0.025. And I get an equilibrium constant of 5. I guess to correct number of sig figs, 5.0 is my equilibrium constant for that one. So if we are given initial concentrations like we were here, we need an ice table to find the change so that we can find the equilibrium concentrations, which are what go into our equilibrium charts when we have initial and one equilibrium concentration calculation. Now this last one is going even a little bit further. So here I have my HBr. And I know this system's at equilibrium. It breaks down into H2 and Br2. Now here I know I have 1 mole, so I have my initial concentration of HBr. I have 1 mole in a 2 liter container, so 1 divided by 2 is 0.5 moles per liter. I don't have any of my products. 0.0 moles per liter. And I have nothing else. Now this is probably the hardest type of question that we'll be asked to do in these ones. And in this situation, we don't know how much they change by. Now, just like in math, we don't know how much something changes by, we use a variable. So H2 I know is going to go up by X amount, and Br2 is also going to go up by X amount. So at equilibrium, H2 will be X moles per liter, and Br2 will be X moles per liter. Now I know that HBr is going to change by twice as much. The reason why I know it's going to change by twice as much is because the coefficient is 2. So HBr is going to go down by 2x. So at equilibrium, my concentration is 0.50 minus 2x. We know Kc in this situation, and now we can kind of build our equilibrium law. So Kc is my concentration of H2 times my concentration of Br2 divided by my concentration of HBr, and that's squared. Now when I put in numbers, so this is going to be 4 is equal to x squared, because it's x times x, over 0.50 minus 2x. And that's going to be squared as well. Now I could, if I want, and if you so desire, you can use the quadratic formula to solve this. The other thing we can do, which is going to be most of the time, is because these are squares, everything is squared, I can take the square root of both sides. So by taking the square root of both sides, I get 2 is equal to x over 0.50 minus 2x. Then I can distribute and solve for x. So I have 2 times 0.50 minus 2x is equal to x. So 2 times 0.5 is 1 minus 4x is equal to x. I have 1 is equal to 5x, and so x is equal to 1 divided by 5, which is 0.200 moles per liter. So if I think back to that ice chart, so my x was the concentration of H2 and the concentration of Br2. So x is 0.200 moles per liter. That is their equilibrium concentration. If I think about the concentration of HBr, well, the concentration of HBr was 0.50 minus 2x. And so that would be 0.100 moles per liter. So this is the most difficult type of ice question where we don't know how they change, so we have to use a variable. Now we're not going to have to use the quadratic formula. If we do have to use a variable, we can take the square root of both sides and then it will work out in that situation. But those are the types of questions that we're doing this in. To using an ice chart and using a variable when we don't know any of the equilibrium concentrations.